So there are just a couple of things that you need to take away from this first section. And first thing is this new function, the exponential function with base a. And the notation for that is given right here. F of x equals a to the x power. And so here we see that the variable x is actually the exponent. So it's important to remember that. The variable is the exponent. The base a has a couple of restrictions on it. First of all, we want a to be a positive number, so we don't use a base equal to 0, and we don't use negative numbers for bases. And secondly, we don't use a base of 1, because if we did, then we would just have the function f of x equals a to the 1 power. I'm sorry, not a to the 1 power. F of x equals 1 to the x power. And, of course, 1 to the x power is just 1. So f of x equals 1 is not really a very interesting function, and doesn't really look like an exponential function anyway. So we won't allow bases to equal 1, but any number greater than 0 except for 1 is a base, can be a base for an exponential function. And now the other interesting thing is that we have x can be any real number at all. So whereas in the past exponents have been, well, when you first started out, exponents were just whole numbers, so you learned about 5 to the first power and 5 to the second power and so on. And then you learned about 5 to the 0 power, and you learned that that was equal to 1, so exponent of 0 gives 1. And you learned then you learned about the alternate way of writing the square root of 5. We can write 5 to the 1/2 power. And so then we learned that when we have a fraction as an exponent, that the exponent is interpreted as the numerator of that fraction is the power of the base, which in this case is 5, and the denominator, in this case 2, is the root. So for example, if you wanted to write the cube root of 4, you could write that as 4 to the 1/3 power. And 5 to the 2/3 power would be 2/3 power, would be the cube root of 5 squared, which is 25. So rational numbers for exponents, but now we allow any real number to be an exponent. So for example, exponents can be numbers like the square root of 2, for example. So you could have something like 5 to the power square root of 2. So that means something, but it doesn't mean the same thing as 5 to the 3rd power means. Like 5 to the 3rd power means 3 factors of 5, 5 times 5 times 5. But 5 to the square root of 2 power doesn't mean that kind of thing. So we're thinking of this now as an exponential function, and we can use a calculator to figure out values of exponential functions. And so if the function is 4 to the x power, you could use the table feature of your calculator and calculate these function values. And so notice that this is an irrational number. Here we have a rational number, 0.5, and then we have a negative value, and here we have a rational number, 1/3. So we are allowing all these various types of numbers now, any real number. We're not putting complex numbers into exponents, no imaginary numbers, but just pure real numbers. So we compared the graphs of 2 to the x power and 2 to the negative x power in class, and we found that the graph of 2 to the x power, let me make some room up here for what I want to do here. Okay, so we found that the graph of 2 to the x power looked like this, has a y-intercept at 1, 0, and it rises rather steeply. So there's the y-intercept right there at 1, 0, and it's got a horizontal asymptote at the x-axis. It's a horizontal asymptote right there, but it doesn't have a vertical asymptote. This gets closer to the x-axis, and this just continues to increase, but it would eventually cross any vertical line you would draw. So that's what the graph of 2 to the x power looks like. On the other hand, now 2 to the negative x power means it's a reflection across the y-axis. So remember, when you use the negative of x, you go across the y-axis. So the reflection across the y-axis will give us, as a graph of 2 to the negative x, we'll get the same y-intercept, but this time the graph is decreasing has the same horizontal asymptote. So you see the two graphs and how they compare to each other. Now, the interesting thing about these two graphs is that they actually show you one important property of the graphs of exponential functions. Remember that the base a can be any number between 0 and 1, but not 0 and not, any number greater than 0, but not 1. So we have 0, which is not included, and then we have 1, which is also not included. Okay? But our base can be any number between 0 and 1, or any number greater than 1. So the interesting thing is that for all exponential functions, if the base is a number between 0 and 1, then the graph of the exponential function, let me just make a little bit more room here, get rid of some of these words. Okay, in this case, the graph of the exponential function is decreasing like that. In the case that the base is greater than 1, the graph of the exponential function is increasing like that. So, and essentially that's what we saw here. The graph of 2 to the x power has a base of 2, but 2 to the negative x power, remember, since that's a negative exponent, you can rewrite that as 1/2 to the x power. So you see that the base is between 0 and 1, and the graph of that function is decreasing as you go from left to right. So that illustrates this property of the graphs of exponential functions, that the exponential function f of x equals a to the x, has domain all real numbers, so the exponent x can be any real number, and the range is only the positive real numbers. The line y equals 0, the x-axis, is a horizontal asymptote of the graph of f, and it has one of the following shapes. It's an increasing function with a y-intercept at 1 if a is greater than 1, and it's a decreasing function with y-intercept at 1 if the base is between 0 and 1. So we can graph these functions, which are transformations of exponential function, and the first one is 2 to the x power minus 3. That's a transformation which is achieved by a shift to the left of 3 units of the graph of 2 to the x. So if this is the graph of 2 to the x, remember 2 to the x, like all exponential functions, base greater than 1, has the same y-intercept at 1, and it's increasing throughout its domain, so it's going up, and it's approaching horizontal axis, or yes, horizontal axis is an asymptote. So if you take that graph, 2 to the x, and shift it 3 units to the left, that means that this y-intercept will shift 3 units to the left. And so the new y-intercept, instead of being at 0, 1, will be at negative 3, 1. 1, 2, 3. Negative 3, 1 will be the new position of that point. So all the other points will shift over, and the graph will do something like this. Okay, so now we are going to have a different y-intercept. If you want to, you can figure out the y-intercept. Remember, the y-intercept is achieved when x equals 0. Oh, I did that wrong, didn't I? I sure did. Now I know that I did it wrong because I'm thinking about the y-intercept and I know what it should be. So this is not the correct graph. Let's just get rid of that graph, which is not correct. So what I wanted to do, I'll just get rid of this. Wait a minute. Just get rid of this. Okay, so what I wanted to do was take the graph of 2 to the x power, and what I did there was I did a shift to the left, and what I should have done was I shift down. This is a shift down of 3 units, because this is occurring, this minus 3 is happening to 2x, 2 to the x. 2 to the x is a y value, so y is being shifted by 3 units down. So what I should have done was take that y-intercept, which is at 1 right now, move it down 3 units. So 1 unit would be to 0, 2 units would be to negative 1, and 2 units would be to negative 2. So the new y-intercept will be here. And the horizontal asymptote also shifts down 3 units, and so the new horizontal asymptote is at negative 3. So there's the new horizontal asymptote. We sketch in the asymptote, and then we draw the graph. So now it has a new x-intercept. That's what I wanted to say. All right, so this is 2 to the x minus 3. 2 to the x shifted down 3 units. So the question is, what's that x-intercept? Well, the x-intercept is a achieved when 2 to the x minus 3, the y value, equals 0. And so we get 2 to the x power equals 3, and at this point we do not have sufficient tools to solve this equation. We can't solve an equation where the variable is in the exponent, and that's going to happen in a couple of more sections. But an equation with the variable in the exponent requires a new technique for solving that we don't have yet. But in the meantime, we can look at an interesting formula which arises out of using exponential functions, and that's the compounding of interest formula. So interest is compounded means that you make an initial investment for a certain period of time. After that time period, you receive interest or a little bit of extra money at a certain rate. And then, if you leave the money in there, they will give you interest on the new amount. So the interest is added on, and then you get interest again. So the interest is compounded because you get interest on the interest. The longer you leave the money in, the faster it grows. So what we want to see is this formula for calculating the compound interest. So the compound interest formula tells us the amount after t years, that's A of t. So this formula tells us how to calculate A of t. A of t says take the value of p, which is the principal, it's the amount you invest, multiply it times this expression, which contains r. R is the interest rate per year, so it's an annual percentage rate, APR. R is an APR, annual percentage rate. And then n is the number of times the interest is compounded per year. So some common compounding periods are annually, so annual compounding, annual, okay, semi-annually, that would be twice per year, semi-annually, okay, and then you can do it quarterly, which would be 4 times per year, quarterly, and then sometimes you can even find monthly compounding. Okay, so in a later section we'll learn about something called continuous compounding, which I don't know of any banks that offer continuous compounding, but we can certainly continuous compounding, we can certainly study it, but in a later section we'll look at that. And then the other variable in here is t, and t is the number of years. Okay, so it's just a matter of substituting the numbers into this formula, and I recommend strongly that you use a calculator, but I also recommend that you do a little simplifying before you put the numbers into the calculator. So I'll show you what I mean by doing this problem for you, or working it with you here. If $10,000 is invested at an interest rate of 3% per year, compounded semi-annually, we want the value of the investment after 5 years. So we're given every variable except A of t, and A of t is the amount we can find. So we remember the formula. A of t is equal to the principal, which is $10,000, so 10,000, times 1 plus the interest rate, 0.03, divided by n, which in this case is 2, because we're compounding semi-annually, and then raised to the power n times t. And again, n is 2 and t is 5, so n 2 times t, 5. Now a little simplifying before we go to the calculator will make this a lot easier. So we'll simplify this to 10,000 times 0.03 divided by 2 is 0.015. And so this is 1.015, and 2 times 5 is 10. So you can enter this into the calculator much more easily. You just enter it exactly the way it is right here. If you don't want to use parentheses, you can use a times multiplication symbol. So when you do that, you'll get the value. So the only thing that's different for these other two parts, for the B part and the C part, is t, the number of years, and so the only difference will be in the exponent up here. So what you can do is you can enter this function, A of t, you can enter it as A of x in your calculator, right? And you can put x up here for the exponent, okay? And then you can just look at the table for x equal to 5 years, x equal to 10 years, and x equal to 15 years. So that will just make it a little easier for you to work the other two parts of this problem.